Okay, so let's go over the collection for probability and walk through the solutions for each. I haven't actually reviewed what I did for this, so it's gonna be figuring it out on the spot. So for question one, we have let A and B be events. Define the conditional probability of A given B, denoted by P, A's, and then this B. So the conditional probability of A given B means this. And it's just basically PA and B divided by PB, where PB is greater than zero. So the 2 points are obviously given as the formula here over here and the PB greater than zero. I think I missed 1 point because I forgot to say that PB is greater than zero. It can't be equal to zero, and probability can't be negative either. So that's a condition I forgot. An easy point. Suppose that PB belongs to 0 to 1, show that PA is equal to PA given B times PB plus PA given B not B times P not B. So basically, this is just the law of total probability, so we can't prove it using that. So we just kind of have to go by the definition. We know that A, any kind of event with the like the omega will always be itself. Because if we cover the whole space, then it would be still whatever A is. So then we have A, we get from A equals A, the sample space, and then we can write omega as partition it between B. So it can either be B or not B. It has to be one of the two and can't be both. So that's why we can write it as such. And if we distribute that over, we get A and B or A and not B, B not. So then since B and B not are mutually exclusive, we can get that PA is equal to PA and B plus PA and B not. So then we can just rewrite this using the conditional probability in part A1 as PB times PA given B plus PBC times PA given BC. So that's how we get to the exact form that we're trying to show, just slightly rearranged, but it's the same thing. Okay, we're done part A. I think this is pretty standard bookwork. And then it's days are either wet or dry. It is dry today, then it will be dry tomorrow with probability P, or wet tomorrow with probability 1 minus P. If it is wet today, then it will be wet tomorrow with probability P, or dry tomorrow with probability 1 minus P. Let Dn be the probability that it will be dry in days from today. Show that this holds. Okay, so basically we have to kind of define what we have. So let our capital D means dry and W means wet. I definitely have to define it clear so that I write it out in words because that I was called out on this during the exam. And then we kind of define our conditional probability of translating that words into actual symbols. So we have PD n minus one, n plus one is given Dn is P and 1 minus P, P 1 minus P. Pretty straightforward, I say. So in part one, what we do is we want to show this. Um, Basically our Dn in this question is just our probability of D of n, the capital D. So we use what we have earlier by law of total probability on day n minus one. We have Dn is equal to P given Dn minus one. So basically conditioning on whether it was dry or wet the previous day. That's what we mean. This is the dry case and this is the wet case that it's dry today. So then we just substitute this in and the composite of that, which is not dry, which is wet, right? So then we just put these values in P, and 1 minus P is from the definition above. So then we get this expression. When we rearrange it, we get to this. And we get show what we need. Basically for this question, because it's worth 5 marks, yeah, definitely more words to answer the question because I got deducted 1 mark for nothing. Okay, part two. Find Dn where n greater than or equal to 0 if it is dry today. Okay, so if it is dry today, that's what we're given. So we have this expression that we got from earlier, like our earlier part, we got this from earlier. So then, what we do is, we set um dn minus, we move this part dn minus 1, and then we leave the constant on the other side. So then we get to this form. Basically, we just rearrange this formula. And then we could just write it in terms of x because it's simple. And we get our characteristic homogeneous equation. X plus 1 minus 2p is equal to 0. And then in this case, um, we would want to set, mm, we just rearrange this because we just kind of set this 1 minus p to be 0 because it's our homogeneous. So then we just rearrange this form to be x equals 2p minus 1. That's our homogeneous solution. And for a particular solution, because we see that it's not a special value, we just set it to be a constant. We call it C. We have C equals 1 minus P plus 2P minus 1C. So that's our particular solution. And we get that C is equal to 1/2. Okay, so going back to our equation, we know that dn is equal to this, our homogeneous solution to the n power plus our particular solution. And then we have our constant here of a that we don't know. So we're trying to find what our constant a is. And we're just going to use the boundary condition that we know today is dry. So d0 is equal to 1. We plug this in to the equation, d0 equals a times 1 plus 1/2. So then our a is equal to 1/2. So then we get our final equation is this. I think this question was relatively simple. And what is the expected number of dry days during the next week? Okay, how I got this question wrong was that I misinterpreted what next week meant. Next week means like basically if today was like Saturday, then the next day is like the next 7 days. Like if this is today, then next week refers to these 7 days rather than the 7 days after that. I thought it was the 7 days after that, but apparently it is it counts as the next day counts as part of this next week. So for this question definitely wants you to use indicators, so that's actually better to solve. What is the expected number of dry days during the next week? Yeah, dry days. So we kind of define an indicator function to make it simple. So we have our indicator function here. 1 if it is dry, 0 if it is wet. So basically we increase the counter if it's, and this is basically a Bernoulli variable essentially because the indicator function is either true or false, which is Bernoulli. So our expected value from this is the sigma, basically we have 7 days, right, of the expected value of our indicator, which is equal to the sigma of d of n when we substitute part 2. Our part 2 we got, where was our part 2? Here. A of 2 should be, huh. This is a great question, but I think that's later on. I substitute this one, that's the next step. Basically, the here is like we have the sigma and then we're finding the expected value of this, which is just the number of days, which is our definition. And then our expected number of days, whether or not it's true, the probability of that happening, like our expected value is dn. That's just by definition of how we define dn. So then we just substitute dn from earlier that we have this equation. We substitute this in, we get this. And then we see that there's constant, so we move the constant in the front, and then we have this expression in the back. The constant in the front is 7 over 2. The right-hand side is a geometric sequence where we have basically from n is from 1 to 7 of this thing. So then that's our ratio. 2p minus 1 is our ratio. So then we can just have 1 minus r to the n divided by 1 minus r times a, which is our initial value. So then we have this expression. And then we just kind of simplify it and we get to our expected value is this thing. Okay, let's move on to the second question. I think the first one was relatively just calculation and understanding what next week meant, which I misunderstood. Second question is relatively easy as well. It's just prob PGFs. We have a random variable x that takes non-negative integer values and has a distribution with probability mass function this. K goes from 0, 1, 2, so on and so forth. In our part A, we want to define the probability generating function, so our PGF g of xs of x. So PGF of a discrete random variable x is the expected value of s of x, right? So g of xs is equal to e of x to the x power is equal to the sigma of from k to 0, because we defined k to start as 0, all the way to infinity of the probability times s to the k. That's the definition of PGF. Okay, part two, we have show that g of x1 is equal to 1 and e of x is equal to derivative of x1, evaluated 1. So we know that g of x1, when we plug it into this form, is just equal to this thing. Because our s is 1, then everything following to the kth power is still 1. So then we just have our probability thing here. So it would just be the sum of the probabilities from k to 0 to infinity. So since our pk is our PMF, so then that's basically the sum of the probabilities, which we know is 1. So then g of x1 is 1. And then why did I write a star continued above? Did I even write g prime of 1? I mean, if I want to show I think I might have missed e of x is equal to g prime of x1. So if I was to do that, that's basically just showing that g prime is the same way I take the derivative of that. So then it would just be moving that thing down, like the k factor over. So then that would just get me to what I need. But I definitely missed this part, so that's something I should include. But I got that on the exam, so that should be good. And then in part three, we have mu continued above. Is there somewhere? Let me see if I have it anywhere. Okay, okay, yeah, I have it here. I realized, yeah, I have it here, over here. Basically, I have this part that I missed out. G prime of xs is equal to the sigma. Yeah, that's what I was talking about. Moving the coefficient up to the front. And now what we have is we still have this, but times k. And this is just exactly the definition of expected value. So we have this thing is equal to e of x. Yeah, that's what I meant. Part three, right, mu is equal to e of x. Suppose that another random variable y has probably mass function qk, or k is also this, defined by this thing. Show that the PGF of gys satisfies this. Okay, so this is just algebra bash, I would say, just substituting what we know. So mu is equal to e of x. There's a random variable. This is the definition of it. Pretty straightforward. Qk is equal to that. Okay, show this. So we know that the generating function for y is equal to the sigma from k to 0 to infinity of qk s to the k. That's just a definition of any random generating function. And then we can substitute the definition of qk directly from this thing. We can substitute it directly inside here so that it matches accordingly. And then next, what we do is we extract out the coefficient, 1 over mu in front because it doesn't matter to the sigma, and we are left with this expression. And we can group the terms so that we just first extract out an s and treat it as a constant. And then that way we see that over here we have this remaining part in the bracket. This remaining part in the bracket looks awfully familiar. This is just g prime of x of s from before, because we're just taking the k power and just taking it out in front. This is just what we got before. So then we can rewrite this as g prime of x of s, and then we have the s over mu constant in front. So that's how we get to this form. Now, moving on to part B. Now we have pk is equal to this. So now they actually give us what the PMF is. For some lambda greater than 0, so that x is Poisson distributed with parameter lambda. Find g of x excess and use it to calculate mu. So I have this. I know that follows Poisson. Okay, great. So I have g of xs. And because before I have p over here, now I just substitute this p to be this value. I move e of lambda, negative lambda outside because it's a constant. It doesn't matter for k. It's not dependent on k. So I have this expression left on the right-hand side. And I see that here I have lambda s to the k divided by k factorial. This is just basically a classic Taylor series expansion of e of x form, where I have sigma of some x to the k divided by k factorial, where my x here is lambda s over here. So then I can just rewrite this in a much nicer form when I realize it's a Taylor series. I can write g of xs is equal to e of negative lambda. This is the front thing. And I can rewrite this in terms of Taylor expression as e of lambda s. So then I just, since it's some exponent multiplication, I just do subtraction above, and I just rewrite this and take out the lambda factor in front, and I get e of lambda times s of minus 1. And then the next part it asked me to do is use g of xs to calculate mu. So I know from earlier that mu is respect to g prime of x with respect when evaluated at 1. So I have this expression over here. I just take the derivative, I plug in s equals to 1, and I get that mu is equal to lambda. Okay, I'm done. This part is really easy when you have the prior part. Part 2, find g of ys, and carefully deduce that y has the same distribution as 1 plus x. Okay, so I'm trying to find g of y. Generating function of y is equal to, from earlier, I know that from the earlier part, I know that g of ys is equal to s divided by mu of derivative of xs. So now I just plug in that, and then I have that from earlier. This is just g prime of x, like derivative. So now I see that the lambda cancels out, and I have g of s is equal to s times e lambda s minus 1. So I'm just gonna now I'm gonna work out what 1 plus x is. I'm just gonna set a variable called z that's 1 plus x so that I have a nicer expression over here so I don't have to write 1 plus x. So then it would just be e of s to the 1 plus x. And I can treat s as a constant, so I just extract it out and it would be the expected value of e of sx. So then that would just be s of g of xs. So then I would just plug in what that is. And I see that it's exactly the same as here. It's equivalent. So it's the same distribution because the PGF uniquely determines distribution, which I should end off. Okay, so that's question 2. I think I struggled with part 2 a bit. And then I also struggled to identify how to use Taylor series expansion to simplify this part. But roughly speaking, I think I did relatively well on second question. It's usually the third question that's relatively difficult, and I think I struggled on 3 because I didn't know double integral that well. So here we have which properties must a function f possess in order for it to be the probability density function of a continuous random variable. So this is probably pretty standard book work. To be a valid PDF, there has to be 2 conditions that must be satisfied that they're looking for. Is non-negativity for all real values. So f of x is greater than 0 for all x and all x are real. And then the second probability is normalization area. So the area under the curve is equal to 1. So basically, if we write it out in mathematically, it would be the integral from negative infinity to infinity of fx dx is equal to 1. Another property that our teacher told us that would be nice to cite would be well-defined, so f is integrable, so then we can just integrate it. So that's basically it for question 1. For question 2, part 2, we have let x have probability density function this thing. We have this thing over here. Find the corresponding cumulative distribution function fx. So we have PDF, and we're now trying to convert it to CDF. So we're going to first write out what our PDF is, this thing. And CDF is essentially the integral of our PDF, right? And then we have, so we write f of x is equal to p of x smaller than x, which is the integral from negative infinity up to x of our thing. So we have fx dt. So we kind of break it down to cases. If x is smaller than 0, because we see here we have 2 cases. When x is smaller than 0, when x is greater than 0. So when x is smaller than 0, f of x is equal to 0. So obviously it's pretty true that f of x, the CDF is also 0. If x is greater than or equal to 0, then we have the bigger fx is equal to the integral from 0. So we're starting at 0 because we already cut off everything before that 0. So it doesn't matter if we start off at what value. So we're going to choose that we're going to start off at x and then 0 of e of this thing, which is basically what is here. copy it over. So then this would just be this evaluated from x to 0. And then this is just taking the derivative of that, applying the boundaries, doing that, and I get that. I split it down to two cases, x smaller than 0, x greater than 0. I think this question was pretty straightforward. I think the only slightly difficult part is actually just like knowing that, okay, yeah, you kind of want to split it down into two cases so that you get a nice 0 rather than negative infinity, which is hard to deal with. Moving on to the third part, let y equals x squared. Um, find the probability density function of y. So we're trying to find PDF of y. Y equals this. Okay, so I wrote down the condition here. We have y equals x squared, PDF y. So we know that for x greater than 0, y is non-negative because if we have something squared, that's obviously going to be positive, like 0 or positive. So we know that p of y smaller than or equal to y. That's basically our CDF. We replace the y with our x squared by the definition over here. So we have p of x squared smaller than or equal to y. So we know that the boundary from here, if we're taking just square root both sides, we know that x has to be between negative square root y and square root y. But we know that in the negative part, it's always 0, so there's no chance that there's anything that's going to happen there. So we can reframe it as the interval from 0 to square root y, so the positive side. And then this is equal to our PDF of f of x to square root y. So then our f of y is equal to plugging in from our earlier expression of f of x. Where is our f of x expression? 1 minus this thing over here, like this here. We just put that in with square root y, replace that x with square root y, and we get this expression. And we just slightly simplify that and we get this. And we know that the PDF is the derivative of the CDF. So we can get that small f of y is equal to the derivative of the CDF, which we just get as this expression. So we can break it down into cases 0, obviously 0, nothing fun happens. And then this is just this expression over here that we get. Okay, part BI. Suppose that z is a non-negative continuous random variable whose expectation ex exists. Show that e of z equals the integral from 0 to infinity of pz greater than equal to z dz. Okay, so for this question, we're trying to I think the idea of this is like the harder part that I was not able to do. So we want to show that e of z is equal to this thing. So we're gonna first start off with what we know. Like if we're gonna take an integral, we have to kind of rewrite pz greater than or equal to z, obviously in some better format. So p of z greater than or equal to z can be essentially written as the integral from z all the way to infinity because we're greater than or equal to. So it's from z to infinity of the f of z of t of dt. So that's just the integral of the area of that. So then we can just rewrite this as the 1 minus f of z because it's just if we're taking the right hand side, then the left hand side is the CDF that we care about, right? So then we can rewrite this as the integral from negative infinity of f of this to the negative, just subtracting the just like whatever the whole thing subtracting the from the left hand side is the right hand side bigger side that we want. So that's basically what we did. So then we have the um, right hand side is the integral, like the original integral from 0 to infinity, and then our expanded part of pz, like this was our original, and the inside when we expanded it out, it was this thing. So it's kind of hard to evaluate this double integral this way. So we definitely want to swap order. So the idea is that if we draw out such a form of z and t in 2 dimension, we can think of it as like whichever place we're summing. And when we sum, we kind of just swap it. So then the when we swap it, we have um something like this. This is just basically we realize that when we want to switch it It's actually limited by t over here. That's what's changed because one is just summing it horizontal, one's summing it vertical. So like our boundary is shaped by that. So inside here we have the integral from 0 to t of f of z dz. So we swapped dz and dt. And then on the outside we still have 0 to infinity of dt. So basically it's just which way we sum. And just the condition slightly changes. And I think it's the best, easiest way to visualize this, just thinking about it two-dimensionally. And then from here, we can see that mm, we can do from our fz of t has nothing to do with these dz because like it's dependent on the t part. So then we can just move that out because since it's independent, we can just move it out of anything and treat it as a constant. So we just have the integral of from 0 to t of dz of f of z of t, and then integral from that to dt. So then we can realize that the thing over here is essentially just whatever it is. So then this is just up to t, so we're gonna have t. And then this was our original expression, so we have it here. And we're now left to one integral. And since it's just one integral and it's just from 0 to infinity times the value times its um what is it called? PDF, then this is essentially the definition of expected value. And since it's the expect f of z, then it's for the variable z. So this is essentially for e of z. And then we have the condition because it's from 0 to infinity, it's for non-negative values. I think this part was definitely quite difficult to show. Some people try to do another method by integration by parts, but it didn't work out for them. And then next we have hence find the expectation of the random variable x from A of A2, part 2. You may find it helpful to recall that the n normal distribution of 0, 1 has density this thing. Okay, that's pretty helpful. Yeah, we're trying to find expectation of random variable of x. Okay. So we know that from BI, we know that expected value of this is equal to that. We know from A1 that we have this, and then we know from here, from BI, we're gonna have to evaluate the P of x greater than or equal to x. So then we can think of this as just like the tail probability, so then it would just be the 1 minus the left-hand part. And then that would just give us this expression as earlier. So then our E of x is essentially just the integral of that, and then we replace P of x greater than or equal to x by this expression we just found, d of x. And then from the hint, we know that the normal density of this thing over here is equal to 1, which is a very nice thing. And our form is somewhat similar, except the fact that we're not from negative infinity to infinity. We're from 0, so we're halfway. And then they have a constant in front. So we realize that this function e of negative x squared divided by 2, because it's x squared, it doesn't matter, it's an even function. So it has to be symmetric. If it's even function, it has to be symmetric. So that means that our half from 0 to infinity is just exactly half of this from negative infinity to infinity. So then our thing would, if we have this expression with the same constant over here, it would be 1/2 if we start off at 0. So then essentially what we have to do is we just put in an extra coefficient of this thing so that it matches that. So we just have another coefficient in front so that this coefficient matches that. And then we just have a coefficient in front. And this probability is equal to 1/2. So then we just have this coefficient times 1/2 is our expected value, which is square root of pi divided by 2, which is a very nice number. And I think that's it for question 2. I think for this question it was quite difficult because I didn't necessarily think of how to replace that 0 over here, like from negative infinity. I did not think of just replacing that. On top of that, it was kind of difficult. I kind of got lost in the section of like keeping track. And then the double integral of thinking about it in the area of counting it either by rows or by columns, and then swapping that is kind of difficult. I did not think of about the solution in the thing. And obviously identifying that it's an even function is definitely really helpful for avoiding the algebra bash that would have taken 2 pages long. So like that's definitely like question 3 was more challenging out of this exam. But I'm think I could have done better on this, but I think let's call it for a day. I could definitely improve. Cool.